Okay. Hello, Fatem and Dr. Jamshidi as well.
Hi, Mortaza.
Hey, Dr. Jamshidi.
Hi,
Thanks for
Mortaza.
selecting this paper. It seems a nice one.
Yes, yeah, it's this paper was submitted at NeurIPS last year, so it's a little bit relevant to our work as well. That's why I chose this one. Hope it would be informative today. um, okay. Okay. Um, Cool. Well, thank you everyone for joining. So today's paper is regarding near optimal multi-perturbation experimental design for causal structure learning. Um, and this is a work by Dr. Uh, sort of led by Dr. Caroline Uller from MIT and two other researchers from ETH. This was, as I mentioned, submitted in NeurIPS of last year. Um, so just a very quick explanation about the title. What they did in this paper is the problem is causal structure learning. So we are given data, observational data, and in some cases we are able to perform experiments or interventions on basically the data. So intervention is also possible. We don't have only observational data. So in this setting, they sort of design an algorithm to find out the causal edges between different nodes um, in the data or between different variables in the data. So it could identify the causal edges, and they do so by sort of near their algorithm they mention is near optimal, and they explain more what that means. And another important thing about this design is it is multi-perturbation. And what they mean by multi-perturbation is they can do multi-intervention. Basically, instead of intervention, they use perturbation here. So instead of doing intervention on one node, basically they do intervention on multiple nodes at the same time simultaneously. So if we take out the multi-perturbation from the title, near optimal experimental design for causal structure learning has been done before by other people, and they reference them a lot. The only value basically they add in this work is they allow for multiple intervention at each time. And there are three papers they reference a lot in their work here, and they use their algorithms and their sort of theorems as well. So I have them here, so we can just take a look at them very briefly. One of them is this paper by Agrawal et al. It's regarding ABCD strategy, budgeted experimental design for targeted causal structure discovery. So this is still causal structure discovery problem, but the focus of this paper is having experimental design under a limited budget, and the budget here is doing number of interventions on the data or on the basically graph that we have. So we cannot really do infinite interventions. So this is a sort of a point they take from this one. This is another paper they reference here, and in their work is budgeted experiment design for causal structure learning. Uh, this group has developed, Qassami et al. Has developed very nice algorithms that they sort of use in their work. And this is the third paper they reference et al. They actually reference is by Mokhtari et al. A stochastic conditional grading method from convex minimization to submodular maximization. There are a lot of good theories and sort of logic and theorems they use from this paper. So they keep coming back to these three papers when they sort of talk about their algorithm. So going back to the main paper, as they mention here, um, the problem is causal structure learning, and what they do here in this work is they sort of design an algorithm for a batch of experiments that each simultaneously intervene on multiple variables. So these multiple variables and simultaneously doing the intervention is the key point in their work that they do here. And they also mentioned there has been a lot of single variable interventions that has been performed. And one downside to this approach that they take for doing multiple interventions is that experimentally very expensive and very sort of algorithmically challenging, because they need exponentially they need to search for different combinations between the nodes to perform sort of interventions, and they talk more about that. They also talk about the sort of the budget. They have a limited budget for performing experiments, and their real world example is about the gene data, and they talk about that a little bit further, gene regulatory networks. And they say for a particular gene, we cannot really do a whole lot of experiments and or interventions. And doing interventions basically on a causal graph, it means like it's like you take that out from the causal graph, and the nodes the nodes that are directed to that particular node would not have any impact on it, because we're doing intervention and we're taking it out of it. And in a real world example like gene regulatory network, if you want to take too many nodes out, then you don't really have a gene to begin with, and it's sort of in a biological perspective sort of messes up the whole experiment design. So that's why they said this is a good example of a budget constraint experiment. And then there are some theories they talk about submodularity properties, and as they later mention, monotonicity of the functions they use. These two properties help them with their algorithms, so they can come up with this near optimal sort of design that they use. So they begin their work by sort of introduction to what is a DAG. Basically, also another important thing they mention is, as I mentioned, gene regulatory network is their real world example. They talk about Markov equivalence class, or MEC. So they talk about this a lot. And it seems like what MEC is that um, when we have only observational data and no intervention possible, we can only identify the true DAG or the true structure of the causal model up to a set of DAGs called its Markov equivalent class. Meaning, let's assume we have a true DAG, a true causal model or a causal structure, but we don't know it, but we know some small portions of it or small parts of it, and those small parts are called Markov equivalent class of that true DAG. And they talk about some of these terminology a little bit more throughout the paper. So they start with that, and also they have a figure 1 here. In part A, we have this is not really a DAG because the edges are not directed, but sort of shows relationship between different sort of nodes that we have here. And in B, they show that two different interventions are being performed on this node here and this node here. And the objective is we want to find out the edges, the direction of the edges between these. So this is their assumption actually here, that we do know the basic structure. So it's not like we don't know anything about the structure. We know the basic structure, but we don't know the direction of the edges or the orientation. And this is what their algorithm helps find out. So there are limitations to their work. It cannot help with start from scratch and find out the full causal model. So they say, for example, these two nodes, if we want to perform interventions, then we can find out the sort of edges between this node and this node, or this node and this node. And in
Mortaza, may I ask a question? Where exactly they mentioned the assumption that they have? So basically, they assume that they have the true skeleton of the structure.
That's what I understood, and they talk about that a little bit further. Let me actually find it. I think it's helpful if we dimensions. So when it comes to assumptions, this is one of them. We will always assume that there exists no unobserved common causes of any. Okay, that's regarding the colliders and things. It should be somewhere around here. This is the second algorithm they talk about. Test evaluation. I'm sure they mentioned it somewhere. It should be a little bit before this section.
Don't worry, we can find it.
Yeah, I will definitely
Yeah.
get to it. I will definitely get
Okay,
to
sure, sure.
yes. But this is my understanding that we do know this, and to sort of confirm that this is the sort of the supplement section. This is like the identify or this is the true tag that they use for the real world data set. And what they mention in the paper is that they know the nodes are there and their relative relationships. They're just interested in finding out the directions. But I'm sure we will get to that.
In the second paragraph, they mentioned at the end that they assume that there is no unobserved confounding variable. That's at least one assumption that they assume.
Yes. Yeah. They don't have a like assumption section where they list all the assumptions. It's just all over the paper. But they do talk about some of the limitations of their work, and I'm sure we will get to it in a second. So back to this figure one, this, for example, if we have these nodes, and if we want to do the same intervention but on two nodes, this is like another case that they mention. And in D, there are 5 different DAGs for the sort of the same MEC or Markov equivalent class, basically. And each of these DAGs correspond to a different root node. So for example, if the white node is here, this is the root node for the remaining nodes that it gets connected to. If it's here, this would be the parent of any nodes that sort of goes after it. And these are different sort of combinations if you want to consider any of these nodes to be the root node. So they talk about that and also talk about the doing intervention on single random variable, which has been extensively used by other people. And what they want to add is multiple perturbation setting, and they talk about how they do that, for example, and they talk about the figures here as well. For example, in figure 1 for B and C, they say illustrate a specific example where two node intervention completely identifies a DAG in half as many interventions as single node intervention. So it's sort of saying performing two interventions saves time, and we can do it with a lot less overall interventions. If we do these two interventions simultaneously, this would save interventions in the long run for a Q node, basically causal graph. But it is exponentially, basically, we need to do the search in a exponential manner because it would be more expensive computationally. So,
Mortaza, would you like to elaborate why the intuition, why doing multiple intervention at the same time on different variables would save time?
Mm-hmm. Yeah, definitely. So my understanding is that if, for example, if we consider this a structure and we want to sort of identify, and as I mentioned in D, if we want to sort of do one intervention at a time on a different node, and let's say that node we want to do intervention on is here, for example, and then we switch to this one, and if we want to find the relationships, it takes sort of 5. But if, for example, and for the same structure, if we want to do multiple interventions, and here the two interventions are of the same type on these two nodes, here there are different types, and as they mentioned here, doing intervention on both of these nodes is enough for us to find out the sort of the edges between these nodes we're doing intervention on and the remaining nodes. Whereas if we want to do single interventions, but in different sort of batches, or in different basically times, we would have to do this 5 different times for each of the nodes that we have. So if we have a structure that has Q nodes, we have to do the experiment Q times for finding the relationship if we want to do single interventions. Whereas if we do intervention on a multiple nodes at a time, then that can be basically a lot. We can come to a decision or come to result a lot faster. So this is how I understood it. I hope I was able to answer your question.
So basically, the doing intervention on multiple variable at the same time, like would save doing unnecessary intervention in the future, right? Because the earlier intervention, especially the combination of two variable, more than one variable at a time, would inform the future intervention in a way that makes some intervention unnecessary, especially with respect to interactions of multiple variables, right?
Exactly. Exactly. And yeah, exactly. And they talk more about how they do the interventions, and as we see in B and C, the interventions are not from the same parent and child. They're from sort of nodes that are basically not each other's parents or children. But yeah, they mentioned this would they would come to finding out the results faster, and actually they showed their results later. Comparison between And for example, and we will definitely come back to this. For example, edge orientation objective, and by edge orientation they mean identifying the direction of the causal edge, and these three algorithms are developed by them as SSGA, SSGB, DGC, and they talk about it. And Q here means number of nodes we're doing intervention on, and Q equal 3 means at each point or at each batch we're doing 3 intervention, or we're doing intervention on 3 nodes, and they compare that to a greedy algorithm with only a single intervention in each batch, and they compare the results, and they change that as well for the different settings. So it seems like this definitely saves time, and it would the algorithm would converge faster this way. After they talk about sort of the overall scenario and what they're trying to accomplish, they talk about sort of like a a background, what the DAG is, but here in a little bit more details. They talk about essential graph, and they talk about this a lot in the paper. They mentioned the essential graph of G, or S of G, is a partially directed graph which with directed edges with all the members of the MEC share the same edge direction, and with undirected edges otherwise. So the Markov equivalent class that they mentioned here, essential graph of G, or let's say G is an unknown causal graph that we don't know the exact edges, but the essential graph of that is a partially directed graph with directed edges where all members of the MEC share the same edge direction. And then the ones that we don't know, the undirected edge, they exist there as well. Then they sort of introduce what they mean by interventions, and sort of they save on P here. It basically refers to nodes in a causal graph, or variables, or as they said, perturbation targets. Intervention I being performed on different nodes. And they sort of talk about 2 different types of interventions: a hard intervention and a soft intervention. By hard intervention, they mean intervening on a set of sort of eyes that basically removes the incoming edge to the random variable, meaning assuming we have a causal structure and we want to do intervention on a node, hard intervention sort of means taking that particular node out of the causal graph. This is like hard intervention, and then they talk about soft intervention later on in the paper, which is, if I remember correctly, not taking that basically out from the paper, from the causal graph, as they have here. Some of the results extend easily to alternative model of soft interventions, as they discuss in supplementary material. Not taking it out, but sort of the conditional probabilities between that node and other nodes would change in a way that the intervention is being performed, but the node is still there. It's not like taking that out from the causal graph. And later on, they come back to their motivating example, which is the gene regulatory network. And as they mentioned, M is the number of interventions that is allowed. So M here is the budget that they have. And as they mentioned, a constraint on the number of perturbations per intervention is natural in reconstructing GRNs, since perturbing too many genes in one cell will leave it unlikely to survive. So they don't want to kill the genes in a cell. They don't want to take too many genes sort of out because they want to do too much intervention. So they talk about the terminology here as well. And as we mentioned, this is one of the assumptions they have for their algorithm. They always assume that there is no unobserved common causes. So they sort of assume that all the causes are observed, basically. This can be for of any pair of nodes in G. This sort of means that they do have good information about the structure. There are no causes that its node is not included already in the structure that they have. And based on the example they showed, how I understood it was that we do have the structure. It's just the direction of the edges, causal edges, that is not known. Also, another assumption that they use is that the distribution of random variables satisfy faithfulness with respect to G. So these are the two main assumptions that they have. And because this is an optimization problem, and as they mentioned it, they want to do near optimal design for causal discovery. Their objective function is to maximize f, and as they explain here, a natural choice f is a function that is applied to essential sort of zeta here. They refer to the zeta as satisfying the constraint on the C is the collection of all the causal edges that was identified by the algorithm. So going a little bit up, I should have covered this before we go to that section. Our goal will be to select a batch of zeta of interventions. So where zeta is a multi-set of some interventions. So the objective function is to maximize a function f that takes as input zeta, which is the interventions that we want to do in each batch. And this function f, they mentioned the natural choice for this is offered by Agrawal et al. And this is the paper that we talked about at the beginning. This function f has been proposed by this group for budgeted experimental design for targeted causal discovery. So they just used their function here for their optimization problem. So this is their main sort of objective, but they have basically sort of divide this into three sort of sub objectives, or three objectives that they talk about. Objective 1, mutual information, or MI. And objective 2, mutual information samples, and they talk about that, and we will get to it in a second. And objective 3, edge orientation, or EO. So their algorithm takes care of these three basically objectives. The first objective, mutual information, MI, sort of is given by this equation here, where y is the set of samples from the interventions. So it's important to know that for each intervention they take samples, and in some places they assume they can take infinite samples, and in some other places they assume that they can only take finite samples. And this is why they have two different algorithms, and as they will get to that in a second. After the related work, they propose their algorithms. One of them is optimizing edge orientation objective. One of them is double greedy continuous, or DGC. Another one is separating system greedy, SSG. And the difference between these is the sampling. One of them is finite, and another one is infinite. And based on the kind of sampling they can do, they use different functions or different algorithms that they use in order to drive that main algorithm. But basically, those three objectives are all met in these two algorithms. It's just the sampling and also the algorithm they use to find the causal edges that are different. So back to the objectives. Um, they also talk about they also talk about the sort of a posterior. So this function UMI, mutual information, is the mutual information between the posterior over causal graph G and the samples Y. So at each step or at each batch, they take samples, and after they take samples, they have posterior information, like there's a prior and there's a posterior before and after doing the sampling, and there's a function here that would sort of take those samples as input, and then it outputs, and that becomes fed to this equation to find the value for f, which is used in the main objective function, in the main objective function. So I don't want to get into too much detail of the mathematics here. They also prove these in the supplement material. But what's important here is um, the infinite sample objectives, and as they describe it here, um, um, to remove the complexity of finding the algorithm that optimizes the mutual information objective. It's difficult because they have to account for noisy observations and limited samples. To remove this complexity, they studied the limiting case of infinitely many samples per unique intervention. So this is another limitation of their work, that they have this assumption as well. It is limited to this case of like we can take as many samples as we want, then this may not be possible in a real world scenario. The constraints given by C, which is the collection of all the um, sort of edges, basically identify collection all the interventions on different nodes that we have. Still stipulate that there can be only m unique interventions, but each intervention can be performed with an infinite number of samples. So this helps them in finding the structure of their causal model, because they can do a lot of sampling. They're allowing themselves to do that. Um, And then they say once we allow for infinite sampling at each intervention, then objective two, this is basically what they have. If they want to maximize objective one, which is here, if they want to maximize that with this assumption, infinite sampling, then this would sort of turn into this equation, as they say here, objective two, or the second objective for their optimization, uh, it would turn like this, and S is the essential graph of G, and they talk about how basically they go about solving it. Then they use a result from Qassami et al. And this is the paper that at the beginning we talked about, budget experimental design for causal structural learning. Um, they say that these groups studied a different objective in the infinite sample setting. The objective seeks to, on average, across possible G, give the current essential graph, orient as many edges as possible. And they talk about R, which would be the set of edges oriented by zeta. If the true DAG is G, the essential graph is given by this. So they change the objective function, the objective here to objective 3, based on the results from Qassami et al. And here, basically what they took from this work was that the goal of the study by this group was identifying as many causal edges as possible, basically based on a limited budget or a constraint, or basically limited interventions that they had. So they were interested in, their objective function was optimizing the number of causal edges that can be identified. So that was their objective function, and they incorporate that here as well. And using this and also the make rules, and they talk about make rules in the supplementary material, they sort of put together their own algorithm. And I'm hoping I can find that assumption that I mentioned earlier somewhere around here. Resulting partially. So their algorithm at the end would show all the edges oriented, meaning all shows the direction for all the edges. And then Agrawal et al. Again, they showed this objective is not consistent. However, this is because they fixed G based on the MEC instead of using most up-to-date essential graph for each batch. And then in supplementary material, they show that the approach they take here makes it consistent. And then for the experimentations that they do, they provide algorithms with near optimality guarantees for objectives 2 and 3, while motivating a practical algorithm for objective 1. So most of their experiments and the algorithms and most of their experiments is for objective 2 and objective 3. Objective 2 being the infinite sample one, objective 3 being regarding the edge orientation, basically, that they took from Ghassami et al. Paper. They talk about related work, which they extensively reference the works that I mentioned. Then regarding their own algorithm, there are two algorithms that they develop. Double greedy continuous, DGC, for optimizing objective 3. The edge orientation objective for greedily selecting interventions to maximize an exponential sum, and they employ the stochastic continuous optimization technique of Hassani et al. So I think Hassani et al. Was this other paper, or maybe another paper from this group that they use the algorithms. So they use algorithms from different groups to create their own algorithm. So DGC is the work by Hassani et al. Also, another algorithm they develop, separating system greedy, or SSG, for optimizing objective 2, which was the infinite sampling one. To greedily select interventions, we use the construction of separating systems, and they reference the work regarding the separate systems to create a smaller set of interventions to search over. So instead of sort of having basically doing intervention on all the nodes, they create a smaller set based on the separating system concept, and that's how they do their intervention in SS, fully orient the graph, and SS being the separating systems. Then they talk about for their algorithm to sort of being guaranteed for near optimality, there are two properties of the objectives that they have, which helps them in accomplishing that, which is one of them is the monotonicity, which I'm sure everyone is familiar with, and another one is the submodularity. So these two properties they use to basically identify to help them with the near optimality guarantees for their algorithms. Then they talk about each of these algorithms or objectives in more detail, sort of using different lemmas and theorems to sort of show how they sort of derive their final equations. In some places, for example, this one, they use exactly what Mukhtari et al. have been using, and this NMSCG is an algorithm that has been developed by this group, so they use their results to basically add to their assumptions to basically develop their own algorithm. This NMSTG by Mukhtari et al. Is used here for the DGC algorithm for finding basically an optimal set of interventions that can be performed on a particular structure to identify all the causal edges. But here they use a different algorithm here because this is an infinite sampling, so they use a different one, SSG. So after they sort of talk about the basically the theories behind their algorithms, they perform experimentations. So I want to spend about 5 minutes or so, or maybe a little bit less, about the experimentation and comparing different results. So and they explain more what they are. So SSG is the second algorithm, DGC is the first one, and then they also use basically for the experimentation they use a sort of random method, and they explain what random method is, and we will get to in a second, and also greedy method. And what is different is that in, for example, in greedy method there's a single intervention performed on a graph at the time, but in B, for example, for all the methods there are two basically the intervention size and the batch size may be different. But in a little bit below they talk about these terminology. So for random in their experimentation, a baseline that for m interventions independently and uniformly at random selects q nodes for those adjacent to at least one undirected edge. So it's a random process to sort of identify a non-direct basically edges based on the placement of the nodes, which as we can understand it's not a very accurate measure. Then there's the greedy algorithm, which greedily selects a single perturbation intervention, as in the work by Ghassami et al. DGC is the algorithm they develop a stochastic optimization approach. And then for SSG, they divide it into two. One of them is a greedy approach using the graph agnostic separating systems of this group. And then in another one, they use graph dependent separating system constructor of this other group. So they sort of divided, they use two different versions of their algorithm based on the work of other people. So comparing the results in, for example, figure 2a, edge orientation objective, meaning the objective being basically finding the causal edges in a graph. And as they see, at the beginning there are some advantages of, especially in batch number 1 and batch number 2, there are advantages in performing multiple interventions and also their algorithm in edge orientation objective. But after several batches, basically all of these methods come to the same result. So it's just about how soon we want to perform that causal discovery. So here batch size was the variable. Here the intervention size, doing one intervention or two interventions or three interventions, and doing and they also mentioned that the SSG B version does not really perform very well with the differing the intervention size. So it doesn't really basically change a lot by changing the intervention size, but the SSGA and DGC, which are the other algorithms they developed, they basically result in higher edge orientation objective, meaning if we have 3 interventions at a time, we would have better results basically, compared to the random method. And also here again the batch size, but here basically edge orientation objective. Um, Let me see what they explain about C. On the difference between C and A is that in C, it's on a different sort of graph. It's on a 20 node forest of 3 disconnected star graphs, and they mentioned that one of them, SSGA, cannot orient the full graph as quickly as alternative approaches. So they also talk about the pitfalls of the method. So the graph used here in C is different from the one used in A. So A, B, and C, on the y-axis, we were interested in seeing the basically better results for edge orientation because it was the edge orientation algorithm. But for D and what for D, we have mutual information objective. So this is their sort of other sort of uh, objective that they use. So in these three, it was objective 2, and here we have objective 3, and here also it shows that the results sort of base we would come to better mutual information objective in less basic in lower number of batches basically, but after 6, 7, or 8 batches, technically even the Grady algorithm would show the same results. Then in E, they talk about the F1 score for different algorithms based on the batch size. And as they mention here, the F1 score for predicting the presence of each edge correspond well with the objective in D. So this is based on the objective they have in D, and this is the F1 score for each of these algorithms. And Q is the number of interventions performed, as we know, Q for greedy only a single intervention, for the remaining one 5 interventions, and they sort of compare the results, and as we see in a lower batch size, better results are obtained. And also finally F, which is for a subnetwork, a yeast subnetwork P50 from the Dream 3 challenge, which was a different, I guess, competition. They used that causal graph from there, and for their algorithm, they sort of they perform 5 interventions at a time, and which would orient more edges in the ground truth stack than random or Q1 greedy algorithms with the same batch size. So here in a real world data set, in a real world causal graph, which if I scroll down to the supplement material, I believe this is what they're referring to, P50 network. And this is, and they provided more information here as well, but performing 5 interventions in each batch would result in better results, or basically lower number of batches required for obtaining the and learning the basically edges in the causal graph. So they have that there. They also provided the data set and code. They talk about terminology here as well. As I mentioned, two different versions. One of them infinite sampling and then finite sampling. And they also talk about this DIM3 network, this real world causal graph that they have, that they use for their experimentation. So I don't want to speak too much. I know we have about 9 minutes left. If there are any questions, I'd be happy to answer.
Thanks, Marteza.
Thank you, Dr. Jamshid. I will definitely look for that section where they mention their assumption on knowing the basic structure. I'm confident they did mention it. I just wasn't able to find it now, but I will definitely send it over to you once I or put it in the channel once I was able to find that.
Yeah, thank you. Yeah, I like this paper a lot, and it is very relevant to your work and also Shahriar's as well. It's a good work. I like especially also the problem formulation, and as you know, essentially this way of intervention is useful for many types of applications. They mentioned gene regulatory, but also uh, like it was few days ago. I've been listening to a conversation with some scientists that were involved in developing um, COVID vaccine. And why in COVID vaccine, why they were able to develop COVID vaccine so quickly, comparing with the other kind of diseases, mainly because of these distributed experiments that they were able to run in multiple different labs all over the world, and learning from each. And this reminds me of, you know, uh, this way of distributed and multiple type of intervention where each lab is doing some sort of intervention, right? And if you compare it with the other intervention in other labs, you could proceed much faster, right? And learn from the data, especially because um, you know, development of vaccine involve lots of variables where there are lots of interaction, especially in genome, right? Um, and the effectiveness and efficacy of it. It this type of you know, distributed interventions are useful. Uh, Not sure what is Shahryar thoughts, whether that he sees applications in multiple interventions in systems too, and whether how this could be relevant. We cannot hear you, Shahryar, if you're trying to talk.
Yeah, can you hear me?
Yes, now we can.
Yeah, I know multiple interventions are like particularly for systems. Multiple interventions are um, actually complex in this case. I definitely think they are useful. I still need to understand better how they can be utilized from the system perspective. Like if interesting, but here, um, bec- yeah, I need to understand better actually. So
I mean, especially for highly configurable system, if you think um, there are many variables and the dimensionality is large, right?
yes,
And exploring the space one variable at a time might not be that effective, right? Especially in a limited budget setting, right?
yep.
But if you know if you can learn from multiple intervention um, to speed up the learning, um, this could be useful, especially because in type of problem that you are exploring, you are learning the structure, so you would like to maximize the information gain with respect to the causal structure. But I mean, learning the causal structure is not your ultimate
Goal.
goal. Is you have a surrogate function that you want to optimize, right? But think about it, this kind of batch intervention could be useful. I mean, especially given existing work that the number of interactions are um, between variable exist and are low dimensional, right?
Yes.
I have one question like, what do they mean by intervening on a variable? So, are we changing the probability distribution and then sampling from, like, uh, as far as I understood, they're sampling from after doing intervention, they are sampling from the distribution. So, like, after intervening, the distribution of the node involved in the network, like, how is it affecting other nodes, that changes, and then one samples from that distribution. So how many number of samples are required to optimize the objective? Am I correct on this understanding, or there is something other than this?
Um, Thank you, Sonam. If I understood correctly, they what they mean by intervention is, for example, let's assume we have this structure and we want to do intervention on this node and this node. This means we assign them values, meaning they're not variables anymore. They would be fixed, and when they would be fixed, then the sort of the conditional independence between this node and its neighboring nodes would be different. And when they want to do sampling, they do sampling on the basically, if I'm not mistaken, on other nodes, and basically comparing it pre and post, basically prior and post, meaning before they assigned the nodes they intervened on any values, what were basically the values, and basically uh, what was the conditional in the independence, and also the distribution for the neighboring nodes, and also after they perform the intervention, how these basically conditional independence change. So I think that this is how they are sort of doing the comparison. I may be wrong, but this is how I understood this.
Okay, yeah, got it. I guess, yeah,
I hope.
that yes, that sounds reasonable. Like, yeah. So the objective, basically, the objectives are defined all over the learn graph after intervention and before intervention. So the objective function should consider all the nodes, not only the intervening nodes, right? So in that case, like if suppose we are changing the values of intervening nodes, so we know like these two values are constant, and if only those two nodes are contributing to objective, um, then they might not have more effect on the objective. However, like the probability, and if we are assigning them a single value, then there so then the probability distribution doesn't come into picture anyway. So if it is a single value or constant, something like that.
Yeah,
Okay.
definitely. Especially because in one of their algorithms, they're allowing for infinite sampling. So I'm pretty sure the uh, unintervened basically nodes are also included in the sampling process. So they keep doing that basically after they intervene on multiple nodes until their algorithm converges with the causal edges.
Yeah, and I think were you looking at the sentence which they mentioned in infinite samples objective on page 3? I think there they assume the essential graph is already known. So in bracket they have written like they have infinite number of observational samples and they know about all the data in experiments. So that's where they are. I think
Which paragraph is on?
in it's infinite observations, like infinite sample objectives, page
Mhm,
3 in
mhm.
middle somewhere. We assume that the essential graph is known.
Oh
Mm.
yeah, yeah, yeah. Yeah, thank you very much, Sona. Dr. Jamshidi, this seems like where they talk about it. We also assume that essential graph is already known, meaning we have infinite observational samples and infinite samples for any experiments performed so far. So they do have the essential graph. It's just they don't know the causal edges between the nodes. So this is another limitation of this. This is not like a starting
But
from
this is in this version of their algorithm when they assume the infinite sample objective, right? Not for the other version, right? Where they have finite sample.
Yeah, so for objective 3, they use some other thing. They use micros to. It seems to be that way. I should be a little bit more into detail on basically what different they use here for object 3. It seems like worked by Agrawal and also micros, but yeah, it seems like here they don't talk about knowing the essential graph first.
Yeah, their code is also available. It would be not sure whether you look at it or not.
I did look at it. They performed a lot of experiments, but yeah, I can take a closer look at this, see what is different here for objective 3.
Try to run it and see whether you can easily run it and test it on dataset. At least they also provided their dataset too.
Yeah.
So
sure. Yeah, we'll make sure to do that. We're a little bit over time. If there are no other questions, I really appreciate everyone joining, and hope this was an informative session.
yeah, thank you. It was. I like the paper, selecting the paper.
Thank you very much.
Thank you.
Have a good day.
Thank you, Murtaza.
Thank you all. Appreciate it. Bye.